All right, hi everybody. I'm just going to keep getting set up here and we'll get started in about 5 minutes. So anyone who's joining the recording, skip to about 5 minutes. I'm just going to give some time for anyone who wants to come live to turn up. All right. Yeah, skip to 5 minutes in the video if you're waiting for the lesson to start. I just want to give anyone who's coming in live the opportunity to come in the next few minutes so they don't miss anything. Hey Aaron, how's it going? Just doing my regular 5-minute wait, so we'll get started in a few minutes. Yeah, nice. Looking good out there? Sweet. How was your evening last night?
It was okay. I haven't actually got a chance to watch those videos, but now that's the weekend, I'll be able to.
Sure. I think there's going to be a new link posted because there was a problem where the recordings we were posting somehow had a password and we don't know what it is. So there's going to be a new link to a YouTube and it'll have all the videos on the one link. So yeah. Yeah, because I have a YouTube channel from Online Practicums, and so I just posted them there and made a playlist of them, so they should all be available in the same place. Sure. Yeah. Give it another 3 minutes, and then I'll get started. It's pretty good. Yeah, mostly it's been a pretty quiet day for me because everyone's on a field trip. I didn't get to go because I had to do this. They're at the wildlife park in Kamloops.
Oh, yeah.
So it's like, I guess it's kind of like a zoo. I've never been, so I'm not sure exactly.
Yeah, I've been there once. I was like, I think I was like probably 7 or something.
Yeah.
22 pounds.
These headphones squeeze my head a little more than I would like. It'll be fine. This is the last time I'm doing this, at least for the current course, so it'll be good. Yeah. If it was like a 40 lesson course, then I would definitely be like, I need a different pair of headphones. Sorry? Yeah, it is. Weekend's coming up. All right, that should be basically our 5-minute mark. So we'll start to get started. So this is our last, I know I'm muted. Go away. It's supposed to be. This is our last lesson of this series. The nice thing about this one is it requires no knowledge from the previous. It's entirely a different thing. We want to talk today about surface area and volume. So finding the surface of a roof, for example, or how much cement you need to fill a particular pad. All kinds of ways this type of stuff comes up in carpentry and construction. The first thing we're going to talk about today is surface area. And so surface area is just like the amount of material needed to cover a given object. How big is the surface of all sides of that object? If you want to think of it as like how much wrapping paper would you need to cover it? If you were giving it as a gift. So some things we need to recall for ourselves are the basic formulas that tell us the area of simple shapes. Most common one most people will remember is the area of a rectangle, just the length times the width, or the base times the height, depending who's telling you and what words they choose to use. A triangle, which is just exactly 1/2 the length times the width. You'll notice that that's almost the same as a rectangle, and that's because any right triangle, I should actually specify that this is a right triangle only. If it's not a right triangle, you have to do a bit of fancy footwork that we'll talk about a bit later. So if you have a right triangle, you can convince yourself through inspection that a rectangle can be made that is the same triangle twice. Okay, so this red triangle is exactly half of the blue rectangle, which is where that 1/2 the length times the width comes from. So that's where that half comes out. And the last one is a circle. One of those we just kind of have to remember for ourselves, that the area of a circle is pi r squared. With all these things in hand, we can actually start to find the surface area of relatively complex shapes. So let's start with one example that I think is on the simpler side. Finding the surface area of this shape. This is a triangular prism because it's a triangle at the base and then it's extruded out and has a height. Okay, so the surface area of this triangular prism, what we have to determine is what sides are there and how many are there of each side. So we have one triangle and two triangles, and I think it's fair to say from this drawing that those triangles are identical. So we can start with the surface area from those triangles. We go 2, because there's 2 of them, multiplied by our area triangle. And I'm going to just leave that like that for now. I'll put an equal sign. We also have a rectangle that is on the underside. We have a rectangle that is on the back and a rectangle that is on the top. Unfortunately for us, all 3 of these rectangles are different. So we need to go plus the area of rectangle 1 plus the area of rectangle 2 and plus the area of rectangle 3. Okay, so we have 2 triangles that we've agreed are identical. And so we only need to find the area of one of them and multiply that by 2. We have 3 rectangles that we can see are all different. So we need to find their areas and add all of those things together. Let's start with the rectangles because rectangles are slightly easier than triangles. If we do the top rectangle first, we'll call the top rectangle rectangle 1. We can see that it has a side length of 5 inches and another side length of 8 inches. So the area of that rectangle is its length times its width, which is 5 by 8. This is equal to 40 inches. What happened there? This is equal to, okay, I've got to calibrate my board. Apologies. Gotta love technology. Woot, woot. This is becoming a theme in these videos. I hope you guys really enjoy watching me press these little cursors in so that they, in theory, know where my pen is at the end of all this. More than I care to admit. Okay, that's better. So 5 times 8, as I was saying, is the area of our top rectangle, and it is equal to 40, and that would be inches squared because we multiplied a number of inches by a number of inches. Inches times inches, inches squared. Okay, we can do now, let's say the back triangle. We'll call that R2. The back triangle we can see has one side length equal to 3 inches and another side length equal to 8 inches. So we have an area 3 by, that's not an 8, 3 by 8, which is equal to 24. And again, this is inches squared because this was 3 inches multiplied by 8 inches. Inches times inches is inches squared. And our last triangle is the bottom, or our last rectangle, sorry, is the bottom one. We'll call that rectangle 3. We can see that rectangle. I hate technology. Go away. Go away. We can see that rectangle 3 has 2 side lengths. One is 4 inches and the other is 8 inches. That is the bottom of this triangular prism. So 4 by 8 is equal to 32 inches squared. Again, inches squared because we multiplied inches by inches. And all that we have left is to do our 2 triangles that we said we had 2 of them multiplied by the area of a triangle. We talked about just a minute ago, the area of a triangle is half of its length times its width. So times 1/2. The length of these triangles, if I use one more color just to make this, is 4 inches by 3 inches of 4 by 3. What we can see here that's kind of nice is 2 times 1/2 is just 1, same as 2 over 2. So those can cancel out. We're left with just 4 times 3, and 4 times 3 is 12 inches squared. Okay, so now we have the surface area of every side on this triangle, where 2 of them are conglomerated into one number, but that's okay because the total surface area of this shape is the sum of all of these. So we've got 12 plus 40, that's 52, plus 24, that's 76, plus 32, that's 108 inches squared. I hope my math is right. I'm going to pull up a calculator really quick and check. So 12 plus 40 plus 24 plus 32 equals 108 inches squared. So we're done. That's our total surface area of this shape. Surface area sucks. It's really easy. You go, yay, surface area, really easy. I know how to do it. But it's a pain in the butt because it takes forever. There's a lot to do because you have to find every surface, and if they're different surfaces, you have to then find everyone separately. If you're really lucky, what will happen is all the surfaces will be the same. Like a cube, for example, is great because a cube, every side is identical, and you know there's 6 sides. So you find the area of one side and multiply it by 6, and you're done, right? But when you get to these sort of oblong shapes that aren't symmetrical, all the sides have different amounts of surface area, so you can't skip any steps by just multiplying them out. I'll erase this before we do another example. I wish I could erase faster, but the smartboard gets mad at me if I erase any faster than this, so. So in this example, we have a cylinder. Cylinders are probably one of the easier but kind of annoying shapes to figure out surface areas for, because they have a weird curved surface that's hard to figure out how big it is. But we can think of a cylinder. Oh, this is not calibrated again. How come? What if I draw it over here? Nope. Okay. Sorry, guys. I've got to recalibrate the screen. I don't know why this keeps happening. It's just as frustrating for me as it is for you, trust me. Okay, so we can think of a cylinder as what we call a net, where we expand it out into only flat pieces. So there's two circles, the top and the bottom. And there's one rectangle that we can wrap around the whole thing. The difficult part of determining the surface area of a cylinder is to determine the dimensions of this rectangle, the side wall, the thing that's wrapped around the circle. What we have to do that is figure out how big this side, I'll use a different color, this side length here must be. Okay, we're given the height of the cylinder, so we know that this side is 15 centimeters. So we have to think about, to do this, our various equations for circles. We know that this side is exactly the same length in a straight line as the circumference of this circle, the line all the way around this circle, because when it wraps around, it meets perfectly on the other end. So this side has to be exactly the circumference of a circle. And if we recall the equation for the circumference of a circle, it is that C, the circumference, is equal to 2 times pi times its radius, or it is equal to pi times its diameter. Either one of these equations works just the same because the diameter is just 2 times the radius. Okay, so those are the identical equation. It just depends whether they've given you the diameter, the full length across the circle, or like in this case where they've given you the radius that's just half. So let's start with that. Let's find our circumference of this particular circle. So we're going to say C is equal to 2 times pi times the radius, which is 8 centimeters. Okay, and C is equal to, pull up a calculator because I'm not doing calculations with pi in my head, 2 by pi by 8 equals 50.26. Let's just call it 50.3 for the purpose of this example. 50.3 centimeters, right? Because we have 2 and pi are just numbers, they don't have any units, and our radius was given to us in centimeters, so our units are going to end up being centimeters. We carry those along with us, and if we multiply 2 numbers with units, we have to also multiply their units. So we have the circumference, which is this length at the top of this rectangle, is 50.3 centimeters. And we know from before that the area of a circle is equal to 2, no it's not, that's the circumference. The area of a circle is equal to pi times its radius squared. In this case, we have 2 circles, a top and a bottom. They're identical, so we can say that we need 2 times the area of the circle, which is 2 pi r squared. Okay, adding to this the area of the rectangle that makes up the sides, a rectangle, this is equal to 15 by 50.3. And both of those are things where we know all the numbers we need, so we can type them into our calculator. 2 by pi by 8 by 8, just because that's easier to type in than 8 squared, is 402.1. And 15 by 50.3 is 754.5. Okay, so we have the area of both circles in this number here, the area of the rectangle in that number there, and that is all the surfaces that make this up. We add it all together, we're going to get 1,156.6 centimeters squared. Centimeters squared comes in this one because we multiplied the radius by the radius, centimeters by centimeters, and in this one because we multiplied the height, which was in centimeters, by the circumference, which was also in centimeters, giving us centimeters squared. And then in this last number, we're only adding two numbers together. When we add numbers, the units stay the same. 2 chairs plus 2 chairs is 4 chairs. 2 chairs multiplied by 2 chairs, well, that's a bad example because 2 times 2 is the same as 2 plus 2. But in any case, when you multiply, you have to change your units. They become squared or they become the 2 units multiplied together. And when you add, you can keep your units the same as long as your units are already matching. And that's this one done. The only trick to this is figuring out this net, figuring out what that side surface takes up. I do wish that we could spend more time on sort of working through the thought process of a lot of these, breaking down these shapes more specifically, but given the nature of this course being so short, I think it's going to suffice because a lot of you guys have done a lot of this before in other courses, to blow through some examples at relatively rapid pace, knowing that you guys will have access to rewatch and replay as much as you need to of these. So some shapes have surface areas that are a pain in the butt, put simply. A good example of this is a sphere. And I think the only example we're going to go through today is a sphere. And that's because a sphere is a shape that might come up fairly regularly, but is still complex in terms of calculation. For the purposes of this course, it suffices to say that this is something we just need to know, that the area or the surface area of a sphere is 4 pi times the sphere's radius squared, okay? You can show this more rigorously, but I would say that that's beyond the scope of this particular course. So for now, we're just going to take this as gospel and move forward with a couple more problems. So one example where it's straight up just a sphere, we remember that the area of a sphere is equal to 4 pi times its radius squared. In this case, we have to be careful. They've given us the diameter, the full length from side to side of this sphere, but we're being asked to use a formula with radius, where radius is exactly 1/2 of that. So R is equal to 9, 1/2 of 18 is 9, and that's in meters. Because we've divided a number of meters by a number with no units, the units then stay the same. Okay, so we go, this is equal to 4 times pi times 8 squared, which is equal to something that we can determine. 4 times pi times 8 equals 804.2. That's not centimeters, this was in meters. Again, close it, close it. 804.2 meters squared. Meters squared again, because the radius is in meters, we've multiplied meters by meters, giving us meters squared. Okay, so that's a fairly simple example with a sphere. When it's just one sphere, it is nice and easy for us because we are just memorizing the formula. As long as we remember the formula, it's just a matter of plugging and chugging. So sometimes surface area gets complicated. We have things like this that we call compound shapes. Shapes made up of more than one other shape. So the reason I say this is because we've talked already about finding surface areas of prisms. We could treat this as 2 separate prisms. One that is they're both rectangular. This is not quite a square because this entire side length is 7 and this side length right here that we're sort of taking away to get the shape up top is 2. 7 take away 2 is 5, and 5 by 4 is not quite square. So two rectangular prisms sort of smushed together is what this shape is. So I'm going to leave this division here, and we're going to say that each side of this shape, so the front side facing us and the back side that's in the board behind there, is made up of two rectangles. So I'm going to say front plus back is equal to, they're both the same shape, so we can say 2 multiplied by the total surface area of one of them. So let's look at the front. This bottom rectangle here has 9 centimeters by 2 centimeters. 9 by 2 plus this top rectangle here. We mentioned briefly that this whole side is 7, and this small blue side that we're taking away represents 2 of those 7. So this rectangle on top, the red one I've just drawn in, is a 5 by 4, where the 4 was given to us in the picture. So we have plus 5 by 4, and that whole thing is equal to the surface area from the front plus the back. We can plug all of that into a calculator. 9 by 2 is 18, and 5 by 4 is 20. So 18 plus 20 is 38, and 38 times 2 equals 76. 76, this is in centimeters, so centimeters squared. That's the front and the back of this particular shape. Now we need to work on the tops, bottoms, sides, and all the rest. There's a whole bunch of them here. So again, this is not difficult, but it's a pain in the butt. I'm going to keep erasing things because otherwise the diagram gets incredibly messy. But let's say the bottom next. So the bottom of this shape is made up of one big fat rectangle. It's got one side that is 9 centimeters and another side that is 10 centimeters. And there would be like a side and another side that you can't see because they're obscured by the image. So area of a rectangle, just length times width. This is equal to 9 by 10, which is equal to 90 centimeters squared. Now we can go from the bottom. Maybe the next best thing to do would be, that doesn't go there, would be the back. So the back of this shape, again, is made up of just one giant rectangle. That giant rectangle has a side length of 7, and it shares a side with the bottom, where it's this imaginary side we just talked about. That side must be the same as the front side, must be 10 centimeters. So we have 7 by 10. This is equal to 70 centimeters squared. Now, if we look at the top of this shape, again, surface area is not difficult math to work with, but man, does it get obnoxious when you have shapes like this. It just gets to be a lot of calculation. So if we go to the top we can say is made up of 2 separate rectangles again. In this case, these rectangles are not the same, so we just have to find both and add them together. One of them is made by this red drawing right here, and the other by this, I'm going to do black, right here. Okay, so I think we can agree that this side is the same as this side is the same as this side, unless this shape has a weird distortion that we can't see. So if that side is the same as that side is the same as that side, then we can say that the red rectangle on the top is 4 centimeters by 10 centimeters. So this is 4 by 10 plus
this black rectangle that's kind of halfway up the whole thing. We have to figure out this whole side is 9 centimeters, and we can sort of think of it as taking away this side of the red rectangle to get what's left of the black one. So that's 9 centimeters take away 4 would give us a 5 centimeter side right here. And we've already agreed that this 10 centimeter side on the front is the same as the other two. So we then have 5 centimeters by 10 centimeters. This is 4 by 10, which is 40, plus 5 by 10, which is 50. 40 plus 50 is equal to 90 centimeters squared. And holy smokes, we're not done yet. This was poor language. I should have said, this is like, this front and back is not the same as the back I've used here, and I was about to say front for this side. Hopefully that isn't too confusing. These blue front and back, I'm talking about the complex shape right here and on the other side. And when I said front and back on this black pen, I was talking about like if these were stairs, the fronts of the stairs and the backs of the stairs. Hopefully that isn't too confusing. Yeah, but now that I'm this far, I'm going to keep it as is, and I'm going to use a black pen to match it up to the other one. I'm going to say the front, in this case, is made up again of 2 rectangles. We have one here, and we have one here. Okay, so the sizes of those rectangles, we've already sort of gone through how to do these. We've got one that's 2 by 10. It's totally given to us. 2 by 10 plus, that's this red one here. This blue one, you can convince yourself is 5 by 10 because this we've already agreed is the same as that front. And this side is 7. Take away the 2 that's already used up from this bottom half. That's 5 by 10. So 5 by 10. This is 2 times 10 is 20, 5 times 10 is 50, 50 times 20 is 70 centimeters squared. Okay, now we just got to add all that stuff together. We have 76, I'll circle these, 76 plus 90 is 166, plus 70 is 236, plus 90 is 326, plus 70 is 396 centimeters squared. Hopefully that's right. You can check in your calculator. If I'm wrong, send me an email and I'll give you a prize. No, I won't. Just kidding. Cool. So this is a mess, but it's easy math. Okay. It's simple steps. It's just taking your time to make sure you've hit them all. Some of you guys may or may not have noticed that this could be slightly simplified. When I'm looking at this shape straight from the top, even though there's a change in height, I could treat this as one big rectangle. Because if you look at this straight down from the top and ignore any difference or shadows, you just see one rectangle. So for this one, for example, I could have just said 9 by 10. I could have skipped finding all the separate rectangles. I wanted to do it out long ways just to show you guys, but what does that mean? If we start to think about this, the surface area of this is almost the same as if it was just one full big box. Okay? These 2 rectangles on the front are exactly equal to the total area of the one big rectangle on the back. And these 2 rectangles on the top are exactly equal to the area of one big rectangle on the bottom. So both of those are much simpler. It's 2 times the area of the bottom plus 2 times the area of the back is like half of our work already done. And then we just have to find the area of this weird shape on the front, the other front. I don't know what a better word for that is. Maybe someone can send me an email and tell me what a better word for the front, that weird shape front versus the left side and right side maybe. I don't know. I hope that it's making sense. Please email me if I'm not making any sense, or I guess it's going to be on YouTube, so put a comment and ask if I'm not making any sense. What time is it? 2:35. Let's skip this example. This is another one of those where it's just taking your time and being careful. I'm going to skip this example just in the interest of time because we still have to go through all our volume examples for today. So calculating the volume of shapes, I think, is easier in most cases than calculating the surface area. It might be a little more confusing to wrap your head around, but I think the math, the actual procedure, is going to be a lot less work in general. Basic formulas to calculate volume of prisms, which is typically what we're working with, is the area of its base. So in a cylinder, the area of that circle on the bottom multiplied by however high you go up. Okay, in a triangular prism, it's going to be that area of whatever triangle multiplied by however tall that prism is. It might be a deep prism, it might be laying on its side, but we still call that length, that distance you've extruded or moved that shape across, its height. So for a rectangle, we have length times width, the area of that rectangle that will make up its base, multiplied by the height. For a triangular prism, we have 1/2 length by width, that area of the triangle that will make up its base, multiplied by a height. Circle, similar, pi r squared, the area of that circle that will make up its base, multiplied by its height. So moving swiftly on to some examples. We have a relatively straightforward one. The kind of interesting thing about rectangular prisms specifically is that any side can be its base because they have that symmetry where every side is a rectangle. This doesn't work quite the same with all the shapes, but for this example, let's choose this side that I've just shaded black. That side will be our base. I'm going to denote the base with a big B, and the base is equal to 2 centimeters by 5 centimeters. Okay, so 2 by 5. The height is whatever distance that shape has to be moved across to represent this whole volume. So if you imagine this base that I've colored in very poorly in black, moving so that the corner moves along this line, it's how far would it have to move until it is sort of swept the whole volume of that shape. In this case, that is 8 centimeters. They've given it to us. That is our height. So you'll notice that even though I'm calling this height, that is not the way this is oriented. It's laying down. In this case, it's a depth. We just arbitrarily use the word height to describe how far we've extruded one of these shapes or swept one of these shapes along, just because it gives us a nice letter to choose. If we didn't have a word for it, it's harder to pick a letter and it's harder to remember what letter is in the formula. It just makes it easier. So we go the base times the height, right? So 2 by 5 by 8. This is 2 by 5 is 10 by 8 is 80. And that is in centimeters cubed. 2 centimeters multiplied 5 centimeters. Centimeters times centimeters is centimeters squared. And all of that was multiplied by 8 centimeters, and centimeters squared multiplied by centimeters is centimeters cubed, right? Just like 2 by 2 is the same as 2 squared, and 2 by 2 by 2 is the same as 2 cubed. Just with units, so letters instead of numbers. I think that should be fairly straightforward, but let's do a couple more examples. I think we do one more that's fairly straightforward and then some compound shape examples. Yeah, this one's a good one. So now we don't get a choice on the base. Because this is triangular, we don't have that symmetry where you can say any side is just swept along to make this shape. So we have to use the triangle as our base. What we'll notice in this particular case is that this triangle that makes up the entire base is not a right triangle. And we only have formulas to find the areas of right triangles. So what they've already started for us in this picture is they've dropped a line straight down from the point such that that line makes a 90-degree angle with the bottom of the triangle. Okay? What this does for us is it gives us two separate right triangles. They don't say this explicitly in this particular example, and it will not always be the case. But in this example, it is meant to be that this is what we call an isosceles triangle, or an equilateral triangle rather, where this is exactly equal to this. So if the whole thing is 6, then half of 6 is 3, and the other half is 3. So this is made up of two identical right triangles, and we can find each of them and add them together, or recognize that the formula for a right triangle divides by 2. So when we multiply by 2, it's just going to get rid of that. Okay? If I wanted, I could take these two triangles that I've drawn here, and this black line in the middle is 5 centimeters. That's given. 5. I could redraw these two triangles in a different way to sort of help visualize this, where this side is 3, that's the right angle. This side is 5, and that is the hypotenuse. And I could draw the other one where this side is 5 and this side is 3. So you can see how this area, which has to be the same as this area because it's made up of the exact same number of the same triangles, is just the area of a rectangle that's 5 by 3. So the area of our base in this case, we can either say is 2 times the area of this triangle, or we can just say it's the area of this rectangle. I'm going to look at it as being the area of that rectangle. So 3 by 5, the base is equal to 3 by 5. And the height, again, is how far do we have to sweep that base, or move it along a given line so that we've covered the whole volume of the shape. In this case, that's this line making up our height. And that line is 8 centimeters. 8. And the total volume is our base by our height, which is 3 by 5, all multiplied by 8. 3 by 5 is 15 multiplied by 8. I think it's 120. Let's see. 15 multiplied by 8, 120. Excellent. Equals 120. 120 what? These were centimeters. We multiplied centimeters by centimeters by centimeters. That's centimeters cubed. Okay. So again, I think volume questions typically look easier. They're just a bit more to wrap your head around. Figuring out the areas of these bases can sometimes be complex, but once you're there, you just multiply by whatever height you have. There are more complex volume geometries, and I think we do talk about one of them in the example of a sphere in this lesson, but in general, you can break things down so that it's just a series of prisms and maybe some spheres. So speak of the devil, just like before with surface area, some shapes are complicated to figure out and justify where these volume equations come from. So we have things like the sphere that we just kind of have to remember, particularly in the context of this course being that it's so short. So the formula for the volume of a sphere is 4/3 pi r cubed, which is where our cubed units are going to come from because our radius is going to be in whatever units of measurement we're using. And we're going to cube that value. So quick example, here we're given a sphere. And again, we should notice that they've given us the entire diameter and we only want half of that to get the radius. So the radius is 4 millimeters. We use our formula for volume, which is 4/3 pi times the radius cubed. This is equal to 4/3 pi times 4 cubed. And we can type that into a calculator, giving us 4 times 4/3 equals that times pi equals that times 4 to the 3. equals 268.08. I'm just going to call that 268 equals 268 millimeters cubed. Okay. Again, sphere is complicated, but we make it easy by just memorizing the formula, as much as memorization kind of sucks. You can always look it up. In real world, you have access to the internet or books or whatever. If you're really, really stuck on this problem, go to pull out your phone, look it up. And then you already have the skills to actually do the math. So let's see, how many more do we have? We have 2 more examples and then we're free for the day. Actually, forever, because this is the last one. So this example looks very similar to the big surface area problem we did that turned into a big giant mess. I think it's going to be a lot nicer in this case. So we have to figure out what side is the base and what side is the height of this shape. Again, I wouldn't call the base the bottom. This is because this shape is consistent through this cross section, this sort of 2 rectangular shape. If you moved that along, you would end up drawing the whole 3-dimensional shape. Whereas if you were to move any other side along an edge, you would draw either some subset of this shape, some smaller object that's not quite the whole shape, or you would draw something bigger than this shape. Okay, so this front side, the side facing us that I've sort of scribbled in blue briefly there, is our big B, our base, the thing that we will multiply by the height to figure out the total volume. And we have to figure out the area of this base. So we sort of have 2 ways to do this. One is to say there is a blue rectangle here and a red rectangle here. Find the area of each of those rectangles and add them together. And the other is to say that there is a red rectangle here and a black rectangle here, and find the area of the red rectangle and take away the area of the black rectangle. I prefer personally to find areas that are there and add them than to find one area that is there kind of and take away another area that is not there. Sometimes that won't be possible, but I think for this example, we're going to be able to find all the areas that are there and add them together. So let's see if we can do that. So the areas that are there, we have this black rectangle, and that is, so this whole side length, actually, let's start with this red rectangle that I'm going to draw right now, because that one, all the side lengths are given. 24 centimeters is that long side, and 5 centimeters over here is the same as this side. So we have that one totally done. The red rectangle is equal to 24 by 5 centimeters, and we need to add on this black rectangle, which is going to be a little more complicated to determine the length, but we can do it. We have that this whole tall side is 16 centimeters, and this red side was 5 centimeters, and we want everything but the little bit of red. So 16 take away 5 is 11 centimeters. And we have that this whole red side here to here is 24 centimeters, and that this part that we do not want is 16 centimeters. 24 take away 16 gives us 8 centimeters. So this black rectangle is 11 by 8, which is equal to a number, 24 by 5. Let's see. Oof, that's going to be 95. No, that's 121 plus 11 by 8 is 88. 121 plus 88, 209. Let's see. 24 by 5 equals that, plus 11 by 8. No. Oh, by 8 equals 208. What did I say? Did I say 209? I think I said 209. That's okay. Equals 208. And this is an area, which is centimeters squared. Now we need to figure out the height. How far does this black rectangle and this red rectangle need to sweep across to make up this whole shape? They've given it to us. It's that 6 centimeters equals 6. So base times height is equal to 208 multiplied 6, which is equal to, no, 208 multiply 6, 1,248 centimeters cubed. Because it's a volume, it's always going to be a cubed. We can confirm if we go back that our units are going to multiply centimeters 3 times. Okay? So again, this example you can see, even though it's the same shape as the surface area, was, I think, easier. Maybe a little harder to wrap our heads around how we got there, but the math was a lot less work than the surface area version of this problem. So one more example before we end off. And it is sort of like a storage silo on a farm, maybe. I don't know much about farms, but I think those things that look like that are on farms sometimes. What do we have here? We have a cylinder, definitely, right? That's this circle and this height. And we have a sort of half sphere, right? We're sort of making an assumption that this is a perfect dome, but I'm going to say that's a fair assumption to say that this is exactly 1/2 of a sphere. Now, we remember that the volume of a sphere was equal to 4/3 pi times its radius cubed. So the volume of a half sphere has to be exactly half of that. 4/3 divided by 2, or 4/3 multiplied by 1/2, is 4/6 pi r cubed. 4/6 can be written in simpler terms. This is equal to 2/3 pi r cubed. Okay, so this is our volume of the 1/2 sphere, and we need the volume of our cylinder. Again, the volume of any prism, where a cylinder counts as a prism, is the area of its base, this circle, multiplied by its height. Hey, this one's actually a height. Good for us. So the area of that circle is pi r squared. Just about forgot that. Multiplied by the height. Pi is just a number that we know. Type it in on the calculator. The radius they've given us, I'll erase this so we can see it, as 2.3 meters. This time they did not give us the diameter, so that's nice. This is 2.3 squared times the height, which again they've given us. This line goes straight to where the sphere starts. So 5.6 meters times 5.6, and this is equal to a number that we can determine. Pi times 2.3 times 2.3, just because I'm too lazy to use the squared button, times 5.6 is equal to 93.0 something something something. I'll just call it 93. 93 meters cubed. Close that. And now we need to use this formula for the half sphere we figured out. So V1/2 sphere is equal to the 2/3 pi times the radius cubed, where the radius is 2.3 meters. We can plug that into our calculator. We go 2.3 to a power of 3 is equal to 12.167. We have to multiply by pi, and we have to multiply by 2/3. So multiply 2, divide 3, equals 25.48. So let's call it 25.5. Equal to 25.5 meters cubed. Last step, just add these two things together. 93 meters cubed plus 25.5 meters cubed is equal to 112, I don't know, let's do it. 93 plus 25.5, 118.5. Okay, so that's our final answer for this example. Again, I think slightly easier than the surface area version, even though maybe slightly more confusing to wrap our heads around. So thanks everybody who's made it this far. It means you've watched like 4 hours of this online. Thanks to Aaron for coming in and hanging out with me. And I'll end that recording right now. And meeting.